the surprising impact of 1% packet loss, for which I would invite Kemal. Kemal is a results-oriented engineer focusing on designing, operating, and troubleshooting large-scale networks. He is passionate about Linux and has a deep understanding of SRE, NRE practices. Over the last 2 decades, he had worked at several large-scale companies applying NRE practices and automating remediation actions. As a principal internet analyst at ThousandEyes, he focuses on research and providing deep and meaningful insights into outages through the lenses of ThousandEyes. Kemal, good to have you.
Hello, everyone. My name is Kemal Sanjta, and I'm Principal Internet Analyst at Cisco ThousandEyes. I came from Southeast Europe, and I'm that person that outbid Corey on those Cisco routers on eBay. When it comes to today's talk, I'm going to be speaking about the surprising impact of 1% packet loss, which is the research that we did at ThousandEyes, for which we believe that it might be actually relevant and interesting for this community. I'm going to try to keep it short. I don't want to be the person standing between you and your lunch. TCP has been with us for a couple of decades at this stage, and it's a research, but it's a very well-researched topic, right? Intricacies are very well-researched. We know about the challenges, we know about some of the solutions, and today, if you are going to go for the network engineering interviewing loop, it's very likely that one of the loops is going to be dedicated to TCP. And as part of our experience and research, we know that packet loss has the negative effect on the flows. So at Cisco ThousandEyes, we often publish about various outages that are happening on the open internet, and more often than not, spike in packet loss closely matches the performance degradation that we see. However, with all of that, decades of research and everything, impact of packet loss is something that we don't quantify often. In fact, it's really hard to quantify it. It's designed to actually work against it, so it's a hard problem. And at network community at large, we tend to look past small levels of packet loss, especially if that packet loss is intermittent, right? If it shows up and goes away. So those are some of the challenges that we have. So if countless TCP dumps and Wireshark sessions taught us anything, that's that TCP has multiple different ways to handle the loss, as part of which we are speaking about the duplicate acknowledgements, timeout, explicit congestion notifications or ECNs, selective acknowledgements, but very large portion of that is being handled by congestion avoidance algorithms, which are going to be the main topic today. So due to the popularity of the internet and pretty rapid growth of the computer networks or Ethernet speeds for that matter over the last few decades, network operators, people in this room realized that early congestion avoidance algorithms such as Tahoe and Renault are really slow at utilizing available bandwidth, especially in higher bandwidth networks. Something needed to be done about the problem, so the congestion avoidance algorithm called Cubic was invented, and for a decade or more, it's been doing this job relatively well. Today, Cubic represents the full congestion avoidance algorithm for every major operating system, be it Linux, Windows, macOS, FreeBSD, and so on. So how it works? There are a couple of different aspects to the algorithm that are quite interesting from the operational perspective. The first one being congestion window adjustment. So Cubic for that employs the Cubic function to adjust the congestion window size. The congestion windows is increased aggressively during the slow start phase, which is kind of ironic because it's called slow start, and then cautiously during the congestion avoidance. It reduces the congestion window sharply upon the detection of the packet loss, which is representing or indicating network congestion. When it comes to window scaling, it adjusts the congestion window size based on the current network conditions, and it utilizes TCP timestamps for fine-grained measurements or RTT, which helps it with the bandwidth estimation. And that bandwidth estimation is then utilized for further steps when it comes to congestion avoidance. The main function of the algorithm is obviously congestion avoidance, and once the algorithm reaches, once the congestion reaches the certain threshold, algorithm switches over to congestion avoidance mode. And during this during the congestion avoidance, it increases the congestion window size gradually, trying to avoid undue congestion, right? And when it comes to packet loss reaction, Cubic does react to packet loss as very sharply, as part of which it cuts the congestion window size pretty dramatically, and we're going to see some of these results a little bit earlier on. The algorithm itself implements this approach called additive increase, multiplicative decrease when it comes to that, which helps it with the dynamic congestion windows assignment. So what did we do as part of this research? So our test methodology was to use 5 Linux boxes. We provisioned them with the Ubuntu 22.04, and we configured Linux hosts to forward packets. It's relatively simple thing to do these days. Every single machine here had the 1 gigabit connectivity between one interface card with gigabit connectivity. And we used static routing, and we tested in 2 simple topologies, which we're going to showcase a little bit later. Given the fact that we had only 1 interface card on every single of these hosts, we needed to use the concept of sub-interfaces, and which required us to use VLANs on the switch that we were connecting these hosts to. The switch that we used for this particular purpose was Cisco 3750. And then we were interested in a measurement of the throughput using iPerf3. Unlike bandwidth, which represents the maximum capacity of the available channel, the throughput is real-time effectiveness of the transmission process itself. So as I said, we tested this in 2 different topologies. The first one is symmetric network, as part of which the forwarding path is exactly the same to the reverse path. And this is very commonly used in enterprise networks due to the simplicity of implementing security features such as firewalls, but also it simplifies the troubleshooting because the problem on the forwarding path is going to be exactly the same place where the issue is on the return path. We also tested in a symmetric network, as part of which the forwarding path is completely different to the return path, and this is something that closely reassembles the flows on the open internet. So the first thing that we did was to establish the baseline, as part of which we tested the throughput without any packet loss. And for the symmetric topology, we achieved 804.67 megabits of throughput and 864.13 megabits in the asymmetric topology. This is pretty normal, given all the configuration and topology that we were operating in. And then we introduced the packet loss. How did we do that? We utilized the TC, or traffic control utility, available on Linux operating system. And that utility has the possibilities to introduce the scheduling, policing, and dropping of the traffic. But more specifically, we were interested in functionality provided by one of the extensions of the TC, which is called NetM, which stands for network emulation, and that has the capacity to introduce the conditions such as latency and packet loss. And that's exactly what we did. And once we started testing, we actually got some really interesting results. So this plot that you are looking at represents the difference between baseline and 1% of the packet loss in the topology that's using Cubic. So the orange line is our baseline, and the blue line represents the throughput that we achieved using Cubic at 1% packet loss. And as you can see here, regardless of the topology that we tested this in, it resulted in 70+% drop in throughput. More specifically, what we got was that at 1% packet loss in symmetric topology, we achieved 235.51 megabits per second. And in asymmetric topology, we achieved 222.49 megabits of throughput, which gives that at 1% of packet loss resulted in 70.7% decrease in throughput in symmetric network topology, while in asymmetric topology, it resulted in even worse, 74.2% decrease in throughput. So these are quite interesting results. We actually tested up to 10%, And it's quite interesting to see here that most of the negative compounding impact of packet loss happens relatively early on at 1 or 2% of packet loss. We visualized all of these throughputs that we managed to achieve in this test. And the most interesting thing here is, regardless of the topology that we actually tested this, is all of this white space between the orange line and pretty much everything else down below that. So given the negative effects of very small amounts of packet loss in cubic-enabled topologies, we were wondering whether there's anything that we can test to see whether there are any more improvements. And fortunately enough, there is BBR. BBR stands for bottleneck bandwidth and round-trip time. It's the congestion avoidance algorithm created by Google, and it's designed to optimize network utilization and throughput by continuously probing for available bandwidth and adjusting sending rate accordingly. So how it works? There are several different aspects similar to what we did and covered with Cubic when it comes to algorithm from the operational perspective. And from that perspective, we are speaking about the bandwidth estimation. So BBR estimates the available bandwidth by measuring the delivery rate of the packets. It also uses concept of pacing to assure smooth transmission of packets without causing any undue congestion. When it comes to round-trip time or RTT estimation, it tries very hard to estimate a minimum RTT of the connection. And those RTT estimations are used to adjust pacing rate, ensuring smooth transmission and reduced latency. When it comes to bottleneck detection, it identifies the bottleneck link in the network path through various techniques like probing for increased delivery rates and utilizing RTT feedback. And this is a really important point, which we're going to cover a little bit later on. When it comes to one of the main functionalities of the algorithm, congestion windows management, it adjusts the sending rate by maintaining two parameters, pacing gain and probing gain, and it aims to achieve a low latency operation. It effectively tries to keep the queue utilization very low at all times. Okay, clicker is not working. So when it comes to key differences between Cubic and BBR, we can actually categorize that in those few different groups, but the first one is congestion window adjustment. When it comes to Cubic, Cubic adjusts the congestion window side based on the Cubic function, and it reacts to loss very sharply. And BBR on the other side, they dynamically adjust the sending rate based on the bandwidth and RTT estimation, avoiding unnecessary loss. When it comes to bandwidth estimation, Cubic relies on the packet loss as the indicator of the congestion, while BBR actively probes networking conditions for available bandwidth and adjusts sending rate accordingly. When it comes to latency operation, Cubic prioritizes throughput over latency, which under the heavy congestion results in increased latencies. And lastly, from the implementation perspective, Cubic, as I previously mentioned, is default congestion avoidance algorithm on pretty much every single major operating system today, while BBR has been designed for use in Google's data centers. So how to enable BBR? It's relatively simple. The important thing here to note is that BBR only needs to be enabled on the sending side of the connection. And here we outline the procedure on how to do it on the Linux operating system. So the first command that we are executing is cat on the proc file system to verify what's the currently configured congestion avoidance algorithm. And in this particular case, we can see that it's default Cubic. Then in order to enable it, we are appending to syscontrol.conf file. The first command is to enable QDisk for fair queuing. And the second one is to actually configure BBR for congestion avoidance algorithm. And we are applying configuration by executing syscontrol-p, and that enables the algorithm. Now, it recently came to my attention that one of the things here might not be needed in future versions or newer versions of kernel, given the fact that QDisk with fair queuing has been moved to the kernel space itself. And lastly, similar to first step, we are getting the proc file system to see whether we successfully enabled BBR. So we did exactly the same thing as we did with Cubic. We tried to establish the baseline without without any packet loss. And we achieved 868.50 megabits per second in symmetric topology and 827.20 in asymmetric topology, which is pretty much in line with what we achieved with Cubic as well. However, the significant difference happens here, as visible on this particular plot, where the orange line represents the baseline and the blue line represents the throughput that we managed to achieve at 1% in BBR-enabled topology. So on average, 1% of packet loss caused 8.5 decrease in throughput, which is significantly better than 70.7 decrease that we achieved with Cubic. More specifically, results are here, 794.06 megabits per second was achieved in symmetric topology, and as I said, 8.5% throughput decrease in topology using BBR, and this is a symmetric topology test, which is a stark difference to 70.7 throughput decrease while using Cubic in exactly the same topology at 1% packet loss. In asymmetric topology, we achieved 763.42 megabits per second, which gives that there was 7.7% throughput decrease using BBR and 74.2 throughput decrease using Cubic. Again, a stark difference when it comes to achieved percentages. We tested up to 10% again, and the most interesting thing here is to notice the values that we got in both topologies for 10%. So as you can see here, we were getting around 750 plus megabits per second, which means that that BBR at 10% was significantly outperforming Cubic at 1%, which is mind-boggling. Before I go to conclusion, actually, I wanted to speak about the production readiness of the protocol. So a couple of companies actually did some production-related testing, as part of which they published the articles about their tests. One of those companies is Dropbox, and Dropbox did a really interesting test, as part of which they tested BBR v1 with BBR v2, but also BBR v2 with the Cubic and Renault. So in their test, BBR v2 performed a little bit worse compared to BBR v1, and this might be one of those rare occasions in our industry where less is better. To the known problem of BBR v1 crowding out Cubic and Renault sessions. So it would just starve them out of the available bandwidth. So it was a significant problem in BBR v1. That problem has been fixed, as I said, in BBR v2. And they tested a BBR v2 and compared it to Cubic and Renault, and it was their production level test showed that it's not starving them out of throughput. This problem of BBR v1 is relatively very well covered in our industry. Jeff Houston talked about this particular problem on many different occasions. Effectively, the problem is that when you are designing one of the congestion avoidance algorithms, there needs to be this delicate dance between efficiency and fairness. So BBR v1 went significantly towards the efficiency, while BBR v2 managed to strike this delicate balance with efficiency, but also when it comes to fairness to other congestion avoidance algorithms. Spotify also did really nice tests, as part of which they configured BBR on subset of their customer base, and their test also indicate production readiness. One of the interesting things here is that they were converting already pre-established TCP sessions to BBR, sorry. Google is obviously using it. They designed the algorithm, so they are using it for all of their flows within the GCP. They are also using it for YouTube and search, but that's no surprise. They designed it for their own use case. When it comes to networking use cases, Cisco Catalyst SD-WAN, when you enable the functionality called TCP optimization, actually enables the BBR on both headends of the connection. And this is interesting from the fact that you are actually getting the benefits of bidirectional traffic enhancements when it comes to that particular SD-WAN. And Netflix is also one of the companies that's using BBR. They haven't published anything when it comes to that, but they were, it has been reported they were closely working with Google to port it on FreeBSD, which underpins all of their technical stack very early on when BBR v1 was in development. So given all of that, it's actually no surprise that this algorithm came out of from one of the hyperscalers. If you think about it, the industry moved towards the white boxes maybe 10 years ago. At least when it comes to hyperscalers, they started designing their own ASICs. Broadcom was producing those ASICs. And if you think about it, those might be 48 by pizza-sized boxes, which are 48 by 100G per interfaces. But those interfaces usually have shallow queuing. So what Google tried to do here is to actually maintain the queue size as much as possible to prevent the congestion. And kinds of it's not really surprised that it came from one of these particular use cases. So when it comes to conclusion, what we've shown here is that even the smallest amount of packet loss has extremely negative consequences on throughput. And that's especially important given the fact that Cubic itself is still default congestion avoidance algorithm on pretty much every single major operating system. In fact, if you get your file system or today on your Macs or Linux boxes, you're going to see that that's the case. Packet loss outcomes significantly different based on congestion avoidance algorithm used. We saw that effectively at 1% cubic results with 70 plus percent throughput decrease, regardless of the topology that you are testing it, and BBR results in less than 10%, which is significantly better. This underscores the importance of monitoring and actually taking action on even the smallest amount of packet loss, regardless whether that particular loss is intermittent or not. And lastly, all of these production tests from these reputable companies indicate production readiness of the algorithm. And if it's ready for them, the question is it ready for us? And the real question is actually, is the BBR future of congestion avoidance? Thank you very much, and please let me know if you have any questions.
Thanks, Kemal. I believe we do have questions for you, so if you can just stay close. Please introduce yourself, your name and the company you represent, and go for it.
Thank you for your presentation. I'm Jeff Haas with Juniper Networks. My day job is working on BGP. So anybody who's worked on BGP for any length of time is very aware of this loss, because a small amount of loss, as you show, we usually see 3% is the magic number for us, is terrible for actually slowing down BGP sessions. Looking forward to playing with some of the new algorithms and see how that actually impacts routing. Do you have any experimental results for something that isn't trying to push the fire hose as fast as possible at the gigabit level, and something that's much smaller? Because one of the things we've seen in the past across implementations over the years is that TCP timers get a little strange if you're not pushing too hard.
We don't have it as of right now, but let's catch up after this presentation, and we can actually have that as a potential idea among other ideas for where this research might go. But thanks for bringing that up.
Thank you.
I have a question online from Matt Pitak, who at this point is not employed. Good talk, Kemal. He assumes you're enabling BBR on both ends of the communication. If you only have access to one end of the connection, have you tested performance if one end uses BBR and the other end stays with the default cubic?
So all of the tests were done as part of which BBR was enabled unidirectionally, so only on the sending side of the connection. So if you, a couple of slides back, if you look at the topology graphs that we did this on the left-hand side, you're going to have the iPerf client, and on the right-hand side of the topology, there's going to be iPerf server. And we only enabled BBR on the left-hand side of the connection on the client side. So all of the tests were done from that perspective. The only example that I actually have where BBR performed bidirectionally was in the example of the SD-WAN using Cisco Catalyst, as part of which then you get bidirectional benefits of BBR.
Great, thank you. Any other questions? I have another one from Michael Sinatra from ESNet. ESNet basically is one of the developers on iPerf 3, and his question specifically is which version of BBR did you use in your work, and are you aware of the current state of BBR version 3 in the mainline Linux and .bsd kernels, which is those kernels yet to be in mainline releases?
And so for this research, we utilize BBRv2, which is the default version that comes outside as part of the deployment of the Ubuntu 22.04. So we use BBRv2. And yes, we are aware about BBRv3, which is going to be subject of the future research that we are going to do on this topic. Most importantly here, actually, what Google did here is they created a version of the protocol for the DCs and for outside of DC use cases. So there are kind of two branches of the protocol, and we are going to compare them. Thank you.
I have no other questions from the online chat.
Did you say you have another one? Okay. All right. So that was it. Thanks so much, Kemal. That was fantastic. Appreciate it.